Hey everybody, limits and differential equations, day number 5. We're going to do a little bit of applications of max-min existence. This topic is typically referred to as optimization. Now I've put a set of 4 steps right here, which we are going to utilize today in order to solve these optimization problems. So for example, here we've got draw applicable scenario, set constraints. This is not always something you'll have to do, but it is something that many times is useful. Number 3 is create a function, and then number 4 is solve and reflect. Now by solve, I mean we're going to be taking the derivative using either the first derivative test or the second derivative test in order to determine a max or min value. And then we reflect, right? And the process of reflecting is just to help us to make sense. Does our answer apply to the scenario that it's given in? A few formulas that we're going to see today, whether it's in the notes or in the homework: volume of a cylinder, surface area of a cylinder, and volume of a cone. Any formula that you do need, you will be given. So let's go ahead and jump into our first example and use this 4-step process. Okay, so let's look at number 1. A cylindrical can with open top has a surface area of 3 pi meters squared. Find the radius and the height of the can that will maximize the volume, and then find the can's maximum volume. So I'm not going to necessarily draw this scenario because it'll take up a bunch of space, but I would draw a cylinder. I know that its surface area is 3 pi meters squared. Of course, be careful because it's an open top. So actually in this formula for surface area of a cylinder, I'm actually going to drop the 2 on the very front because that represents 2 circles, top and bottom, but now I only want 1 because it's open. Okay, and I'm just going to take and now in number 2, I'm going to look at the constraints. Okay, and the first constraint is that I'm working with a surface area of 3 pi. Okay, so 3 pi is equal to pi r squared plus 2 pi rh. Okay, now notice that I'm working with 2 variables. And the other formula that I want to work with, and I've got a misstep here on my formula, is I just want pi r squared times h. I want to relate these 2 formulas, okay? So right now I've got volume, which is pi r squared times h, in terms of both r and h. So I'm going to solve for either r or h in the first formula, and then use that with volume in order to solve my my situation, my scenario here. So the constraint that I'm given here is this. And of course, I know both r and h. Another portion of the constraints is that r has to be greater than 0 and h has to be greater than 0. There's really no upper limit on that, or lower limit other than 0. Okay, so I'm going to choose to solve for h and write v in terms of r. So I'm going to write v equals pi r squared times something, and that something is going to be h in terms of r. So the first thing I would do is I would drop all pi's by dividing by pi. So I get 3 equals r squared plus 2rh. Now I'm going to solve for h. So I'm going to subtract r squared. So it'll be 3 minus r squared over 2r. So that's h in terms of r. Let's plug that in over here. Okay, now I've got my volume in terms of the radius. So let's expand that just slightly. Volume with respect to the radius. And now I'm on to step number 3 here. I'm creating my function in terms of only one variable. That would be if I distribute. Notice that I'll get a reduction here of r squared with r. So I would have 3 pi r over 2 minus pi r cubed over 2. Okay, so If I want to maximize the volume, what I want to do is I want to find where the change in the volume with respect to the radius is equal to 0. So now is when we employ the derivative. Okay, so I'm going to take the derivative of v of r. Okay, so my first term is a constant, so I'll get 3 pi over 2. My second term, I'm going to get 3 pi r squared over 2. Okay, now I set this equal to 0, and while I do that, I'm actually going to factor out a 3 pi over 2. So I get 1 minus r squared. Okay, so my critical value here will be r equals plus or minus 1. Now clearly, r cannot equal a negative number, so r will equal 1. Okay, now what does that mean? That means that my volume is maximized. Okay, it's maximized when my radius is 1. How do I know it's maximized? Well, because the second derivative would equal a negative 6 pi r over 2. So volume, second derivative of volume with respect to r would be negative 3 pi r. Now, since r is always positive, then the second derivative would always be negative or less than 0. That means it'd be concave down, and the first derivative would equal 0 at r equals 1. Therefore, there would be a maximum for the volume when r equals 1. Now, if h is equal to 3 minus r squared over 2r, then h actually also equals 1. So the volume is maximized when both the height is 1 and the radius is 1. So we take now in number 4, and I'm going to plug in for the volume, actually back in terms of both r and h. I'm going to plug in a 1 for r and a 1 for h, and it looks like the volume of this cylindrical can being maximized would be pi, what is it, centimeters? Am I working with? No, meters cubed. And that'll happen with a radius of 1 and a height of 1. Okay, number 2. A piece of wire 80 centimeters in length is cut into 3 pieces, 2 equal circles and a square. Now, I will sketch this. So number 1, I've got 2 equal circles. What that means is their perimeters will be equal. I'm not guaranteed that the perimeter of the square is equal to the perimeter of the circles, but I do know that the circumference of a circle is 2 pi r, and the perimeter of a square, I guess I could call, I don't care, 4s. Okay, so you can see what we're working with here, right? So we're working with 2 circles, their perimeters, and 1 square, its perimeter. Now in number 2, the constraints that I'm working on here aren't necessarily that, r has to be a certain length. I mean, clearly r can't be greater than 40. Actually, then you're kind of getting into the weeds. So I don't really care about the constraints on the variables. I just know they have to be positive. Okay, but I do have one specific constraint. I know that 80 is the total of the perimeter of those 3 objects. So since I have 2 circles, it'd be 4 pi r plus 4s. Okay, so I know 4 pi r plus 4s is equal to 80. Now, in this case, what I want to do, just like I did in the last problem, is I want to solve for one of those. Since it looks like I want to find the radius in the problem, I'm going to solve for s. So to solve for s, I subtract 4 pi r, and then I divide by 4. So that should be 20 minus pi r. Okay, so now I have s in terms of r. So in number 3, we can see that we want to find the radius of the circles if the sum of the areas is minimized. So the area of the 3 objects would be 2 circles, which would be 2 pi r squared, plus 1 square, which would be side squared. So the area in terms of r alone would be 2 pi r squared plus 20 minus pi r squared. Notice how I substituted 20 minus pi r for s. Okay, so what we can do here now, of course, is our next step is, since we want to optimize area, I'm going to take the derivative. Okay, and I take the derivative here. Instead of expanding, don't do that. Just use the chain rule. So the derivative of the first term will be 4 pi r. The derivative of the second term will be 2 times the quantity 20 minus pi r to the first times a negative pi. Okay, use your skills in chain rule in order to do that. Let's clean this up just a little tad. So that'll be 4 pi r minus 2 pi 20 minus pi r. All right, now what we want to do is we want to set it equal to 0. Okay, I'm going to set it equal to 0 and expand it at the same time. So it'll be 4 pi r minus 40 pi plus 2 pi squared r. All right, so now I want to solve for r. Okay, so I'm going to clear out all the pi's. So I can divide by pi everywhere. That gives me 4r minus 40 plus 2 pi r. All right, now it's pretty simple. I'm going to do a little subtraction as well as division. So I'm going to add, I'm actually going to add 40 over to the left and factor out an r, which would leave me with 4 plus 2 pi, and then divide by that. So r would equal 40 divided by 4 plus 2 pi. Now this would be complete and totally fine if you left your answer that way, but in simplest terms, this would be 20 over 2 plus pi. Okay, positive value for r, which is what we were looking for. The problem does not ask for the minimized area. So it asks only for the value for r that minimizes the area. Okay, again, I didn't show the second derivative test here. However, if we have a minimum here, then a double prime would have to be greater than 0. And I'll leave that up to you to verify that. But again, here's a different scenario for an optimization problem. I'll just finish it off with when r is equal to this, a, or the area of the 3 objects is minimized. All right, let's look at another example. Okay guys, long one here. Let's get to it though. The production of X number of USB flash drives made by a company can be modeled by C of X. You can see that below here. The projected selling price is modeled by P of X. Okay, and the projected revenue is modeled by R of X. So R of X is always the number of units times the projected price per number of units. Okay, so let's start this off. And this question kind of leads you through the 4-step process, so I didn't put the 4-step process on here. So let's just start with A. It says find the domain of P of X. Well, if the projected selling price is P of X, then clearly we would want P of X to be greater than 0. Otherwise, what's the point of trying to produce these flash drives? Okay, so that would mean that 7 minus 0.002x is greater than 0. Okay, so let's solve for this. If I subtract 7 and then divide by negative 0.002, you notice you'll have your inequality flip on you. And just for reference throughout this problem, 0.002 is the same as 1 over 500. Okay, so 500 times 7 is 3,500. So in order for our price to be greater than 0, we have to produce more than 0 USBs and less than 3,500. Okay, let's move on to part B. Okay, so part B says, find the break-even point or points of the production of the flash drives. Okay, so break-even, first of all, revenue is not profit. Profit, of course, is revenue minus cost. Okay, so your your break-even points will be when your revenue is equal to your cost. Okay, when your revenue is equal to your cost, you've got a break-even point. So we're going to take revenue, which is X times 7 minus 0.002x. Cost, of course, is 500 plus 3x. Okay, so I'm going to skip a problem here. I'm just distributing x as well as subtracting 500 plus 3x over to that left side. And I get negative 0.002x squared plus 4x minus 500. I'm saving myself some space here. Okay, now I'm going to multiply everything through by 500, and actually negative 500, because that'll take care of my leading coefficient. So I'll get x squared minus 2000x plus 250,000. Okay, and using, unfortunately it's not factorable, using the quadratic formula, I get the opposite of b over 2a. So negative 2,000, the opposite of that is 2,000 over 2 times 1. So I get 1,000 plus or minus, okay? And if you take b squared, okay, if I took that, squared it, I get 4 million minus 4ac, which is minus 1 million. I get the square root of 3 million over 2a. Now what this ends up being is the square root of 3 million. Well, square root of 3 million is equal to the square root of 1 million times the square root of 3. Okay, and what happens there is the square root of 1 million is 1,000. And when I divide that by 2, I get 500. So x is equal to 1,000 units plus or minus 500 root 3 units. So my break-even points are both at 1,000 plus 500 root 3 and 1,000 minus 500 root 3 USBs. Okay, so you might be wondering, should I be able to do this without a calculator? That's not necessarily reasonable. This technically is a no calculator problem, but I don't think it's reasonable. Okay, let's move on to part C. State the flash drive production levels in the form A is less than X is less than B that must be met in order for the company to make profit. So of course profit, like I said earlier, is R of X minus C of X. Okay, so in order for us to profit, what we want is for R of X minus C of X to be greater than 0, right? Our revenue greater than our cost. Okay, so we know what P of X is. P of X was actually this function right here. Let me highlight it in red. Right, that's R of X minus C of X. So I want to know where negative 0.002x squared plus 4x minus 500 is greater than 0. Well, I know where it equals 0. It equals 0 both at 1,000 minus 500 root 3 and at 1,000 plus 500 root 3. Now, just looking, I could test intervals, and I'm going to tell you right now, it'll be positive in between, it'll be negative on the outer skirts. And the reason I know that is because this is a quadratic with a negative leading coefficient, right? So its max value will be halfway between those 2 points. I might be giving something away for later, but I don't really care. Okay, so I know that the profit will be greater than 0. Okay, so P of X greater than 0 when X is between 1,000, whoops, I don't want plus, I want minus 500 root 3, and X is between 1,000 plus 500 root 3. And that's the number of units. So provided we're between there, profit will be positive. Outside of those, negative. And you might have already picked that up from part B. Okay, part D. Okay, it says find the max profit that the company can make. So not just how many units will maximize profit, because we know that. We know P of X is maximized at X equals 1,000 units. Okay, so what I would do then, and technically you should probably take the derivative of P of X, find where it equals 0, show it's a maximum. I'm not doing that here. You can do that on your own. But P of 1,000, if I use my calculator, comes out to be 1,500. Okay, I don't know if that's dollars, euros, protein bars. I don't even know. But I know that that's our max profit in whatever units that is. Okay, guys, there's yet again another example. We got a couple more, and then we'll call it a day. Okay, very interesting example here. Let's just get into it. A gardener plans to enclose 3 sides of a 1,000 square meter rectangular plot of land with shrubs. The shrubs cost $15 per meter. The 4th side of the plot of land will be fenced. The fencing costs $3 per meter. Determine the dimensions of the plot that would minimize cost. Hence, find the minimum cost to enclose the plot. Okay, so let's draw. Okay, I'm going to draw myself a rectangle. Okay, I know that in a rectangle, opposite sides are congruent in length. And I know the area of the triangle, or the rectangle, excuse me, is 1,000 meters squared. So to me, that means 1,000 equals x times y. Okay, now I'm actually going to solve for y here. And if I solve for y, I get 1,000 over x. That's going to be useful here in just a minute. All right, so constraints. Just generally speaking, x and y have to be positive, right? So number 2, x has to be greater than 0, y has to be greater than 0, and I'm going to say that y equals 1,000 over x. Okay, number 3, let's create a function. We have to create a cost function. Okay, so how I'm going to create a cost function, and I'm going to move myself over here to the left side, is the cost is going to be 3 sides of which will cost $15 per meter. Okay, this is the shrubs. Now I'm going to write this as 2x plus y. I'm going to just say that one of the y sides is going to be fenced. And it doesn't really matter. You could have x be one of the fenced sides. But that fenced side will only cost $3 per meter. Okay, now I'm going to replace every y with a 1,000 over x. Okay, so then now I have the cost function in terms of x only. So that's 2x plus 1,000 over x plus 3 times 1,000 over x. Okay, let's clean that up just a little bit. So the cost with respect to x will be 30x plus 1500 over x. And then I'm going to add 3000 over x. So I'm actually going to, 15,000 over x plus another 3,000 over x. So I'm actually going to change that to 18,000 over x. Okay, now I've got c of x. Now you might be tempted to get a common denominator to do all that stuff, but if you do that, you're going to have to use the quotient rule. And I don't want to use the quotient rule, so I'm just going to take the derivative right now. Okay, I'm going to find c prime of x. It's going to be 30 minus, now this is using the power rule. Imagine this is 18,000 x to the negative 1. That would make that negative 18,000 x to the negative 2, or over x squared. Okay, so there's our derivative function. All right, now I'm going to clean that up and make it a little bit more compact. Finding a common denominator, that would be 30 x squared minus 18,000 all over x squared. Now, if I want to know where that equals 0, the only thing I really care about is the numerator. So I'm going to factor out a 30. And I get this. This is relatively simple to work with, right? So if I were to take and solve this, I would get two critical values, right? I would get positive and negative square root of 600. Okay, clearly I know that x cannot be negative. So in actuality, like if you look at this, I could test values, or I could see clearly that c prime of x cannot equal 0. That's going to be a vertical asymptote. And then anything negative obviously is out, right? So no negative values. If you test, you could test, for example, just plug in a 1, find c prime of 1. C prime of 1 is going to be negative. And c prime of, well, the square root of 600, that's like 25-ish. So if I plugged in a 26, I'm actually going to get a positive value. Okay, so c prime goes from negative to 0 to positive. That tells me that that's a min value. Okay, so I know that c of x has a minimum at x equals square root 600. Okay, that's great. That gets me almost exactly what I want, right? So number 4. This makes sense to me. R is positive. I've shown using the first derivative test that c has a minimum at x equals square root of 600. Now all that I need to do is find the minimum cost. So I got to find the cost if x equals the square root of 600. And I'm not doing that craziness without a calculator. But if I took c of the square root of 600, I come out to get, using 3 sig figs, $1,470. Got them. Okay, guys, there you go. One more example, and that'll be it for today. All right, ladies and gentlemen, this is number 5, probably the most challenging of the 5 examples for today. Left it for the last one because of just kind of its importance. Seen it a few times on some exams. But yeah, let's get started. So you are 2 kilometers offshore in a boat. All right, so we're going to draw this. Number 1. Here's your boat. It's an awesome boat. Okay, you're 2 clicks off the shore. Okay, here's the shore. And the shore we're saying is a straight line. Okay, the coastline is a straight line with a town. Here's your town. Oops. 6 kilometers. Okay, this distance here is 6 clicks. You are able to row at 2 kilometers per hour. I guess that could be a constraint, right? Row at 2 clicks per hour and run or jog at 5 clicks per hour. Okay, determine where you should land your boat in order to reach the town in the shortest time possible. Okay, so let's visualize this here. You could row, take you an hour to get to shore, right? 2 clicks an hour. And then run or jog, right? That would take you an hour and 12 minutes. So 2 hours, 12 minutes, right? Or we could take a different route. We could row a little bit longer to a point X kilometers downshore and then jog the rest of the way. So how could we optimize and minimize, in this case, the time that we'd be on the boat? All right, so with that being said, since this is a nice right angle there, I'm going to use the Pythagorean theorem to tell me that this would be x squared plus 4, square root of that. Okay, so let's take this idea, okay, of, well, clearly x, let's put some constraints on x. X has to be greater than 0 or equal, and less than or equal to 6. And so we know that x is going to be a value somewhere in there. Let's create a function for time. Well, I know that distance equals, speed equals distance over time. Right? So what is time? I want a time function here. Time would be distance over speed. So time in this case would equal our distance. What is our distance? Our distance would be, we're going to travel along that green line, square root x squared plus 4, plus, what would this length be? Green length would be 6 minus x. Okay, so plus 6 minus x. Now time brings in a new dimension. While I'm traveling along that green dotted line, my speed, okay, is 2. So notice I've got distance over speed. This is my distance, this is my speed. I've got my distance, and of course on this portion of the function, my speed is 5. Okay, so I've got t of x. T being time, distance being the functions on top, and speed being the denominator. Okay, so let's find t prime. Okay, the derivative of the square root of x squared plus 4 is going to be 1/2. And the square root of x squared plus 4 will be the square root of x squared plus 4 in the denominator times 2x in the numerator. Okay, chain rule. The square root function can be written as x squared plus 4 to the 1/2. We bring the 1/2 down. We reduce the power. This would be x squared plus 4 to the negative 1/2. We bring that down as a positive 1/2, and then multiply by the derivative of the inside, which is 2x. If you don't understand that, let's talk. Okay, the derivative here in the second term, this would technically be 6/5 minus x over 5. This would be, instead of, well, I shouldn't have a plus there. This would be plus a negative 1/5. Okay, now I did forget one thing, I believe. Yeah, I did. Oof, wow. I forgot this too. So this would actually make this 1/4. All right, so let's keep rolling. So t prime of x would actually equal, I'm going to reduce this, x over 2 square root x squared plus 4 minus 1/5. We're going to set that equal to 0. I'm going to move my work up here. 0 equals x over 2 square root x squared plus 4 minus 1/5. So I want 1/5 to equal x over 2 square root x squared plus 4. Cross multiplying, I get 5x equals 2 root x squared plus 4. I'm going to square both sides. The intent of that is to get rid of the radical. So I get 25x squared is equal to 4 times the quantity x squared plus 4. So it'd be 4x squared plus 16. I'm going to subtract 4x squared. That gives me 21x squared is equal to 16. So x squared is equal to 16/21. That means x is equal to 4 over the square root of 21. Okay, so in this case, x equaling 4 over root 21 will be the distance that I want to aim for downstream from my boat to head toward, thus minimizing the time that I would spend traveling to the town. And the town probably has a awesome gym that I'm looking for, right? So that actually ends up being, to 3 sig figs, 0.873 kilometers down the shoreline. Now the question doesn't ask me for the total distance traveled or the total time traveled. It just says determine where you should land your boat in order to reach the town in the shortest amount of time possible. Okay guys, that is optimization. A couple of good problems in the homework, so get to them. Let me know if you got questions. See you in day 6.